Hi everyone, welcome to CS 11737 Multilingual NLP. My name is Sachin Kumar and I am a teaching assistant for this course. And today we'll be talking about unsupervised machine translation. Now, before we get started, let's have a brief overview of conditional text generation, where the task is to generate a text output Y according to a given specification X. There are several examples of this in NLP. For example, if you're given a text in English and you have to generate its translation in Hindi, you have machine translation, which we have been studying for the past 3 lectures. If you have an image and you have to generate its caption, that's image captioning. You have a document, you have to summarize it with summarization. If you have a speech input and you have to transcribe it, that's speech transcription. So these conditional text generation tasks are modeled using conditional language models, where you usually have an encoder and a decoder. You encode your input, whether be it text or image or speech, using this encoder architecture and generate a hidden representation. This is passed on to a decoder network, which generates the output text one token at a time in a recurrent manner. These decoder architectures could be RNNs, could be transformers, could be CNNs. But to learn the parameters of these models, you use maximum likelihood estimation, or in other words, you need supervision to train these models. By supervision, I mean parallel data. For example, for translation, you usually need millions of parallel sentences for a model to work well. So the question we're going to ask in this lecture is, what if we don't have any parallel data? There are several tasks, both in NLP and computer vision, that can be modeled like this. For example, if you have a photo of a person or a place, and I ask you to generate a photo, regenerate the photo in the form of a painting, for example, by Picasso, that would be image style transfer. And it's very difficult to find data of this sort, right? Like you can't generate data where the source is a photo and the target is a painting. That would be very, very expensive. Or if you have an image of a person who's stereotypically male and you want to transform into an image of a person who looks stereotypically female, it's gender transfer. Or, for example, if you have a text which is written in an impolite manner, you want to write it in a more polite manner, you have formality transfer or politeness transfer, rather. Or even for translation, if you want to translate, for example, English to Sinhalese, where you don't have much parallel data available or any parallel data available. So you have machine translation, but here without any parallel data to train the model. A natural question to ask at this point is, if you don't have parallel data, why can't we just collect that parallel data? But as I said, for a lot of tasks, it is impossible to collect. First, for things like translation, you need professional translators, which can be very time-consuming and very, very expensive. Even for a task like image style transfer, like photo to painting, that task is just impractical. So like you can't specify, or it's very difficult to specify what to generate. In an example of that in text would be if you ask someone to write text like Donald Trump, or an even more difficult task, like if you ask someone to write text like Stephen King, for example, no one apart from Stephen King can possibly write like Stephen King, right? It's like, first of all, very difficult to specify what to generate, or if you can specify, it's very difficult to evaluate those quality of generation. And even if you can evaluate the quality of those generation, asking annotators to generate such text usually doesn't lead to high quality generations. So like asking someone to write text like Stephen King would not be possible because, you know, the author has their own style of writing. The annotators, I mean, have their own style of writing. So a person who writes such text would have their own style influencing the style they are trying to imitate. So most humans are not capable of of style transfer in text on their own anyways. So with this motivation, we'll look at unsupervised machine translation in this lecture. So in the past two lectures, we looked at how we can use monolingual data to improve an MT system. When you have parallel data also available, or how can we reduce the amount of supervision? Or in other words, what if we don't have enough supervision? How can we leverage monolingual data to improve an MT system? What in this lecture we'll look at is, what if we only have monolingual data? What if you don't have any supervision? Is it possible to learn an MT system in such a setting? So with that motivation, this is the outline of this lecture. So first we'll look at some core concepts in unsupervised MT, like initializing the model, iterative back translation, bidirectional model sharing, denoising autoencoding. And then we'll look at how parts of these concepts are used to build a statistical unsupervised MT model, or how all of these can be used to build a neural MT model. At the end, we'll look at some open problems in this area and some issues remaining in this area, and how the research in the past couple of years have made some advances to address some of these issues. Okay. So step one in machine translation, an unsupervised machine translation, is initialization. So one thing to note here is that when you have monolingual data in a source language and a target language, the task for the model is ill-posed. So like the model is expected to, given a source sentence, generate a sentence in target language. But without parallel data, you don't know that we are telling the model doesn't know that it's being told to like preserve semantics, for example. So providing the model a good bias is a prerequisite for unsupervised MT. To add a good prior to the state of solutions we want to reach, or in other words, to kickstart the solution with like approximate translation of subwords or words or phrases even. So like if you as a person are given two languages which are unrelated, and without just looking at like two corpora of the two languages, it's very difficult to learn to translate between them. But if say you're given a dictionary, you would be able to do some word level matching and probably figure out how to translate from one language to the other, if not perfectly, but in a rudimentary manner. That's what the goal of initialization is. The hypothesis it is based on is that a context of a word in two different languages is often similar, because both the languages typically refer to the same underlying physical word. So the word cat in English and Italian is referring to the same entity cat, and could potentially occur in a similar context in both the languages and in both the corpora. So a good way, based on these contexts, a good way to learn an unsupervised word translation model is using word embeddings. So as I said, like you are given monolingual corpora in both the source and the target language. So you want to learn, first of all, you want to learn word embeddings in both the languages. So for example, if you have English and Italian as the two languages you want to translate from into, you learn, for example, a word-to-vec or a fast-text model for both of them. And the red space, say, is the space of English word embeddings. The purple space is the space of Italian word embeddings. So what we want to learn is bilingual mapping between the words of these two languages, that is word translations. And the hypothesis we start with is that you can transform a word embedding in one language to the other using an affine transform, which in other words, it means that these two word embedding spaces are isomorphic, that they can be transformed into one another using a linear transform. So you are given an embedding X, you multiply it with a matrix W and you get Y. So if you are given, say, a parallel dictionary between those words, you can easily train this model by, minimizing some kind of distance between these two vectors. But this is an unsupervised setting, so you're not even given a parallel dictionary between the words of two languages. So what you do, what we need to do is find out a way to do unsupervised word translation. So this paper by Lampel et al. Does exactly that, using adversarial training. So suppose the two embedding spaces we want to align are aligned. And if you train a classifier to distinguish between a vector of English and a vector of Italian here, if the embedding spaces are aligned, a classifier should not be able to tell if those two vectors belong to separate languages. And that's the exact idea you will use to train W. So you use this classifier or a discriminator to tell whether two embeddings are from the same embedding space or not, and you use this signal from this classifier to improve W, to fool the discriminator using the gradients of the discriminator. And the authors of this paper show that using just this adversarial approach, you can get a good enough seed dictionary or a good enough set of parallel word translations, which you can in turn use to train a supervised word translation model. So you start with an adversarial setting, learn some set of word translations, and then you use those word translations to initialize a supervised model, and then you learn another set of word translations. And you keep on repeating that until you have convergence. So like you will reach a large set of word translations, which are good enough, and beyond which you can't increase the set of good word translations. So that is about initialization. Now let's look at back translation. So back translation was already introduced by Graham in one of his lectures as a way of data augmentation for a lot of MT tasks, especially useful for low resource MT. For example, if you want to translate from French to English, and you have some parallel data from French to English, and you also have some monolingual data both in French and English. So what you do is train a reverse translation model from English to French on using this parallel data, and then translate the English monolingual data to French. Now you have parallel data from French to English and some pseudo-parallel data from noisy French to actual English. So you combine all of this data together and then train another model from French to English. And then you do the same in the opposite direction and train another model with the back translated data from English to French. So you can keep iterating this process, keep improving your model by using the augmented data to make the model better, and then using the better model to augment it again. So like by doing this second iteration of augmenting, you're improving the quality of your augmented data. That's why you're improving the quality of your translations from the model which is trained from that augmented data. So this iterative back translation is used to improve the accuracy of your model. So we'll see now how we can use initialization and this back translation to do unsupervised MT. So first we'll look at how we can apply these to non-neural, that is statistical MT, which is not as popular now, but was state of the art a few years ago, but made a recent comeback in 2016 and 17 when these papers came out. So before we go to unsupervised statistical MT, let's briefly review what is statistical unsupervised MT, which is called phrase-based machine translation. So for example, if you have to translate from German to English, what you first do is split your German sentence into phrases. So these phrases don't have to be linguistic phrases. They can be any n-grams. What you do then is translate each of the phrases individually to English, for which you need a phrase table, a table of phrase translations. And then you will have a sentence which, is sort of looks like English, but is not fluent. So you reorder these phrases using like something called a distortion model and a language model to get the English sentence. Now, this model needs two things: phrase translations and phrase reordering. So for phrase translation, you need parallel data, especially like back in the day when this was proposed, you needed parallel data to learn these phrase alignments. For phrase reordering, you only need monolingual data because you just want to train a language model. Now that we have this background of what statistical MT was, let's look at what unsupervised statistical MT is. So as I said, like you need phrase alignments, which were learned from parallel data. But now, like we saw, like in the initialization step, that you can get word alignments or word translations from just monolingual data by training word embeddings. That's exactly what these papers do. You start with unigram, bigrams, and trigrams of your monolingual corpus. You learn word embeddings or phrase embeddings for all of them in the monolingual corpora, and then using adversarial training, you map these embeddings into the same space and learn phrase tables. So like if all the embeddings are in the same space, you start and say you're translating between German and French or German and English, you pick up a German phrase, you find its nearest vector in the English embedding table, and that would be your English German phrase alignment or a phrase translation. You don't just do nearest neighbors, you also look at the top k nearest neighbors. So you maintain a list of k nearest neighbors so that you have some stochasticity in your model. Now that you have phrase tables, and you also have monolingual data from which you can learn a language model, you can just train a phrase-based MT system just with these two things, the phrase table and the language model. But you can go even a step ahead of this. So once you have trained, a phrase-based MT model in both directions, from German to English and English to German, you can do back translation to augment or to create pseudo-parallel data from German to English and another pseudo-parallel data from English to German using the two phrase-based MT model that you just built. And then once you have this pseudo-parallel data, you can train another supervised SMT model. And you don't need to stop there. You can keep going and keep training or refining your MT model. So that's what's called iterative refinement here, until you keep improving your results on your validation set. That's what these papers show, that if you start with just an unsupervised phrase table, you get not bad blue scores. These are non-trivial blue scores. But if you keep iterating using back translation, you keep on improving these scores to a really high value. So like you go from something like 17.5 for French to English to 27.16, which is a pretty big deal. Right, so that is how you can apply these two simple techniques to do statistical MT, which has been shown to work pretty well. Now let's look at how, along with these two techniques and a couple of other things that I mentioned in the outline, you can do neural MT in an unsupervised manner. So the first thing, or rather the third thing that needs to be modeled here is bidirectional modeling. What that means is that you use one single model to translate from source to target, and the same model to translate from target to source. It's the same concept as multilingual MT, where you want to, maximize transfer between the two languages. So if you're translating from, say, German to English, you provide a language tag, or in this example, say if you're translated from English to French, you specify a language tag at the beginning of the decoding to tell the decoder that it needs to translate into French, and if you are translating from English from French to English, you specify an EN tag, like an English tag at the beginning of the decoder to specify that you need to translate into English. So that's bidirectional model sharing. And then, as I said, like initialization is very important. So you take this model and you initialize the word embeddings of the encoder and the decoder with shared word embeddings that you have. So that way the model has some bias, to share some information between the two languages. And you are doing more sharing by sharing the encoder and decoder. So now let's look at how you actually train this model. So you have a shared encoder-decoder model. So the first thing you need to train this model to do is generate fluent language. And that is done through this denoising autoencoder objective, which is one of the 4 concepts that I discussed in the outline. So what that means is that you start with a sentence in your source language, you add some noise to it, any kind of noise. You can swap the words, you can drop the words, you can add some words, you can switch out words. There are multiple kinds of synthetic noise you can add to your sentence. And then you use the encoder of your model to encode that noised sentence into this latent representation, Z source. And then you pass the source tag, the same tag, to the decoder, and then try to regenerate the sentence. So you train this model by trying to regenerate the original sentence from the noisy sentence. So the reason for doing this is to teach the model to learn the structure of the source language. So you are going from something noisy, which is like not a proper structure, to a proper structure. So the model is learning to add some structure to the language, to learn some structure about the language. It's like learning to do language modeling to generate a fluent sentence. And so that's about fluency in the language. The second thing you need to teach the model is to do cross-lingual transfers. That's done through back translation, like we discussed about. So it's the same principle as before. You translate your target sentence to source, and then you have a source target pair where the source is noisy because it's been translated into. You start with source and the target, and then you try to train the model to translate this noisy source to a real target because you started with the real target. So you go to this target sentence. Sorry, you have this translated source CY. You go pass it through the encoder. You get some latent space, and then you try to regenerate the source sentence. So this teaches the model to do some like cross-lingual training. So the first objective is about fluency. The second objective is about cross-lingual transfer. And the logic, or like the reasoning behind how they work is that the cross-lingual embeddings and a shared encoder gives the model a good starting point. So like if you are encoding, say, this English sentence, I am a student, and then this French sentence, which means the same, using the same encoder in which the embeddings are also shared, the hope would be that the encodings that these two sentences would generate would be approximately the same, because everything else is the same. The encoder is the same, the embeddings is the same. So these should be approximately the same. So if these two are exactly the same or approximately the same, whatever tag you provide here if the language model or like the denoising encoder does its job, then the model is just looking at the exact same vector. So whatever language you want to generate, and it should be able to generate that language irrespective of whatever the input was. So you want to make the decoder, invariant to what the source language was. And this paper goes one step ahead and tries to enforce that explicitly using a third objective, an adversarial objective. So example, you have this autoencoder example, you're trying to autoencode I am a student. So you get some hidden vector for I am a student. And you also have a back translation example. So you have this example, you translate it into English and then you want to translate it back. So you also have another hidden vector. So what you want to achieve is that these two hidden vectors should be indistinguishable. So you train a classifier on the encoder vector, which takes this as an input and then tries to predict whether the encoder input is from which language. So you want to train it to predict which language the encoding is from. So if you can predict it, then that means that these encoder vectors are not in the same space, but you want them to be in the same space. So you use the signal from the discriminator, you use the gradients from the discriminator to update the encoder using this third objective such that they're aligned together as well. So now you have three training objectives: denoising autoencoding for fluency, cross-lingual training using back translation, and then you want to have the encoder vectors together. So you have another objective, adversarial. It's noteworthy that the third objective is not used in all the papers to this, but it's been introduced by this Lampel et al. Paper in 2018. So let's look at some results. So this figure shows the blue score on these 4 language pairs. And on the x-axis, you have like number of parallel training sentences. So these horizontal lines are when you don't have any parallel sentences. So like you have blue scores hovering around 15. And the other lines show like if you keep on increasing the parallel sentences, the performance keeps on increasing. So the thing to note here is that without any parallel data as well, these models perform better than when you had a little bit of parallel data, like from 10,000 to 100,000. So one of the claims of this paper was that the reasoning of this paper was that unsupervised MT can be used as a baseline or like a lower value against which to judge machine translation models. So like a machine translation model should be able to perform as well as an unsupervised model. So having parallel data should only improve the model, not hurt the model. So for example, here the having parallel data is actually not performing better than having no data at all. No parallel data, I mean, at all. Okay. So that's unsupervised MT, at least from those 2 papers in summary. So, initialization in these models is very important. You want to bias your model to a good starting point so you can not get stuck in a weird place. If you start randomly, you will never improve. So you have to start at some good point. Second thing is that you need a lot of monolingual data because you need to train embeddings. You need to train a language model, like using the denoising autoencoding objective, or just the language model in statistical MT. Or you are doing and the third thing you do is, which is the most important, is iterative refinement. So like as we saw, like just starting with initialization doesn't work very well. So you need to do some noisy data augmentation. You like generate noisy or pseudo parallel sentences and then fine tune your model on those and keep on doing that in an iterative manner. And that has been shown to show a lot of improvement. Okay. So now that we have study the basics of like what unsupervised MT is about, let's look at like where it fails, and what advancements have been made recently to address some of those issues. So when does an unsupervised machine translation model work? So it doesn't always work. It only works in what is called a sterile environment. So the papers that we were discussing before, which came out in 2018 at the same time, they did experiments on English, French, and German. And so these three languages are, similar to each other. They're written in the same script. They have, some lexical overlap as well, like, or some, and similar grammar as well. And large monolingual data sets are also available for these languages. So the experiments that were performed in these papers, they were not technically monolingual corpora. They took parallel corpora and then they shuffled the sentences. So they are comparable corpora in the same domain. And the test sets are also from the same domain as those monolingual corpora. So recently some work has been done which show that, if you have less related languages, or if you have like truly low resource languages, unlike English and French, or like diverse domains between the monolingual corpora, or like between the monolingual corporas and the test sets, or if you have less amounts of monolingual data, these models don't tend to perform very well. For an example of this is like if you translate from Sinhalese to English, a supervised model would have a BLEU score of 7.2, but an unsupervised model has a BLEU score of 0.4, which just means that the model generates incomprehensible garbage. So what are the reasons that it does not work in those settings that I just described? So Graham summarized it very nicely in a tweet here, that if you have truly low resource languages, then you have smaller monolingual data. Like monolingual data is also hard to come by. So you get bad embeddings. You need millions of words or hundreds of millions of words to train a good word embedding model. So if you have bad embeddings, you have bad cross-lingual embeddings. And if the languages are, diverse, if you are distant, if they have different morphology, then the assumption that the word embedding spaces are isomorphic, that they can be linearly transformed into one another, is also not very true anymore. So bilingual lexicon induction is also hurt. So initialization is bad. And if initialization is bad, then the model performance will be bad as well. Also, like if the corpora are not comparable, if you don't have data sets in the same domain, then things like back translation will also not perform very well. So these are the open problems in unsupervised MT, or things that still need addressing. You don't have, if you have diverse languages or diverse domains, then it does not perform well. I mean, it's true for MT in general, but it is even more problematic for unsupervised cases. So what you need is better cross-lingual initialization, because different domains of the source and target will hurt cross-lingual initialization. So there's been work using pre-trained language models, which tries to address some of this, but not all of it. Also, what if very little monolingual data or no monolingual data is available? So no is a pretty hard setting, but maybe if you have a very little monolingual data, what can be done? So there has been work in multilingual MT, if you have a low resource language, it helps to have a high resource language, using which you can pivot to the low resource language. That's the homework 2 of, or assignment 2 of this class, where you're supposed to use a high resource language to help a low resource language to do in doing machine translation. Or as we'll see at the end, parallel data for many languages is not as hard to come by, but additional monolingual data for those languages is even harder to come by. So, a tiny amount of parallel data can sometimes be more useful. To do semi-supervised learning, like Graham discussed in his class on data augmentation. Okay, so now let's look at some advances in this area where different initializations have helped, or like using different languages along just to in addition to just bilingual MT has helped as well. So first I'll go through better initialization. Like how can we improve, like as I said, initialization is the most important part of unsupervised MT. So how can we do better there? And an area where this has been the most explored is using language models. So like earlier we saw that you have monolingual corpora, you train word embeddings and align them, and you only initialize the word embeddings of your encoder-decoder using those embeddings. But what these papers do is use a language model to initialize the entire encoder and decoder instead of just the embeddings. So you start with just a BART-like model. So like if you're doing masked language modeling, so you have a sentence, you mask some of the words in the sentence randomly, and then the model tries to predict those masked sentences, and that's masked language modeling. It's been shown to work very well in a lot of monolingual tasks. So what cross-lingual language model is you train the same model but on multiple monolingual corpora in many languages. So along with position embeddings here and token embeddings, you also add language embeddings. So here it's like the language is English. You can also add like a French sentence and add French language embeddings and train this model on both English and French together. And the vocabulary of these models is trained using BPE. So like you learn a subword model on both the languages together. So what ends up happening is you have a lot of shared subword vocabulary, which helps with a better initialization because some of the words are exactly the same in both the languages. And after you have trained this model using the smart language objective on the monolingual corpora, you initialize both the encoder and the decoder of the model that we discussed before with these two trained models. And now the rest of the steps are exactly the same. You have a denoising autoencoding, you have an iterative back translation, and you train the model in the exact same way. So there have been other works where you slightly change the initialization using a different language modeling objective. So, for example, another recent work in 2019 was masked sequence-to-sequence models, which have been shown to work good for both supervised and unsupervised MT. So the objective is still masked language modeling, but now instead of having just an encoder, you have an encoder-decoder model. So you mask some of the words, you encode the sentence, and then you try to predict the masked words, but using a decoder instead of using an encoder, instead of just predicting at the every encoding step. So once you have this, and again, you train this model on both English and French, for example, if you're doing English to French translation, or you can even train this on multiple languages together. So it's a multilingual mask model. And then you initialize the encoder with this encoder and the decoder of your unsupervised MT model with this decoder, and then do the exact same back translation and denoising autoencoder. Another more recent paper, which works slightly better, is a multilingual BART model. So it's the pre-training objective for initialization is also denoised autoencoding. So in a monolingual setting, what that model is that you take your input, you add some noise to the input, and you try to regenerate the input using the decoder. So like mask also does, so like masking is one way of adding noise to your input. What this paper does is instead of just masking, it also does other things like swapping words and phrases, or if you have a document, shuffling the order of the sentences in the entire document, which they have shown for monolingual setting works pretty well and has shown improvements of a lot of monolingual tasks. What this recent paper shows is that you can do the exact same thing for multilingual setting. You just add language-specific tags in your encoder and the decoder, and it works even for cases when the vocabulary is not shared. So once you have trained this, denoised autoencoder using multiple monolingual corpora, you can initialize the encoder and decoder again of your unsupervised MT model and do the exact same steps as before. And so these three initialization so each of them has worked better than the before, but better than the earlier on improving the scores that I presented in the beginning. So it has improved the scores on like these technically high resource languages, English, French, German. It has also shown improvements on like Nepali and English, Romanian, and a couple other languages as well. So this is about initialization. So there has been some recent work on trying to address the issue that sometimes you don't have much monolingual data to begin with. So as I was talking about, like English Nepali, for example, like you won't be able to find a large monolingual corpora for Nepali, but maybe there's a way to leverage a related language to do that. So one of the methods of doing that is, when you have a pre-trained language model, you can train a pre-trained language model, for example, on English, Hindi, and Nepali. And if there is good enough monolingual data in Hindi, so like you can share information in Hindi and Nepali and have that as a way of initializing your model. So like you're like transferring information from a relatively high resource language into your language of interest to learn a better cross-lingual model to do initialization. But what this recent paper proposes is not just making use of monolingual data in the related high resource language, but also making use of some parallel data in source and that high resource language. So that's what they call unsupervised multilingual machine translation. So let's assume I have three languages, X, Y, and Z. And I want to translate from X to Z. And I have parallel data in XY, but only monolingual data in Z. So an example of this could be I have parallel data, for example, in English, Hindi, and I have only monolingual data for Nepali. And the monolingual data is also not very large. So what you do is you like pre-train this model using this mass language objective that I described before. So you have monolingual data in both, in all X, Y, and Z. So you can pre-train mass in all the three languages. So you already have some, information shared between the two related languages. And then you fine-tune or like train your model in a slightly different way than what I described before. So you still have autoencoding, the denoised autoencoding. You still have back translation. So like given an input X, you are translating it into Y, and then you're trying to regenerate it. That's back translation. And that requires only monolingual data. But you have another objective called cross translation, where you use parallel data between, X and Y and do cross translation through Z. So what you do is you translate X to Z and then maximize the probability of generating Y through the translation of the Z. So you're doing it through, you're translating from English to French through Romanian in this example, for which you do need parallel data between English and French. But since it's a high resource pair, you can get access to that data, and maybe you don't have parallel data for Romanian. So this has been shown to improve translation quality for dissimilar language pairs. Like English and Romanian maybe are more dissimilar than English and French. And this paper, for example, shows that you can train a massively multilingual model, not that massive, but like a still a language model with many languages. Some of them are related, some of them are not, and improve translation quality for translation into these low resource languages. One thing to note here is that you still don't have parallel data from Nepali to English and Sinhala to English in this example, but you're still improving. You go from like 0.1 to 7.9 in this example, which is pretty good. Right. Another question to ask here is, like we started with the assumption that you don't have, what if you don't have parallel data? But how practical is that scenario? Like, are there really cases where you don't have any parallel data? I mean, there are some cases like that, but for those cases, you also don't have monolingual data to build anything. But for many languages, you could say that if you can have high amount of parallel data, you also have certain amount of, if you have high amount of monolingual data, you also have certain amount of parallel data available. Because there is like two corpus. One is called one is called JW300, which is a huge corpus, which has like, I think hundreds of languages, and the Bible corpus, which has, I think, more than 1,000 languages. So you do have some amount of parallel data available in many, many languages. But that doesn't mean that you have good monolingual data for those languages. So, so since some parallel data is available, like I think a better way to go about those languages is semi-supervised learning that Graham talked about. So even though like unsupervised MT is like scientifically interesting field, like you want to do translation without parallel data, is still not like, for many, many languages, still not as well performing as if you have some parallel data, which is true for many language pairs, that you can get some amount of parallel data. So with this, I would stop talking about unsupervised MT. One thing at the end I will note is that a very related area to this is where unsupervised approaches are very strictly necessary, is style transfer in text, right? So here you want to rewrite the same language, rewrite text in the same language, but in a different style. Like I described in the beginning of this lecture, if you have, text which is impolite, you want to rewrite as something which is polite, would keep the original meaning. So you want to preserve content, but you want to change the style of writing. Several examples of this are here. So you want to translate something which sounds relaxed to something which sounds annoyed, or something which is written by an adolescent, and compare it to like someone, and translate it to someone, something written by a person who is older, because they're from different times, they would use different vocabularies perhaps. So here are some of the techniques from unsupervised MT have been proven to be useful. For example, in this paper, multi-attribute text rewriting, where they use iterative back translation as well as denoising autoencoding to do style transfer. So if you're interested, you should check that out. Okay, so at the end, we have the discussion question. So the discussion question for this class is that you have to pick a low resource language or a dialect, anything you want, and you have to argue whether you can use unsupervised MT to translate to or from English with this language. If yes, why do you think that's true? And if not, what could be the potential solutions to address that? You know, like you can take hints from one of the previous slides, and you should read this paper. When does unsupervised MT work? Provided in this link, that'll give you some hints to why or why not unsupervised MT can work for the language that you pick. That's about it. Thank you for listening.